Hi, welcome to this lecture. We will continue learning mathematics in the context of biology and how to use mathematics as a language to express the phenomena or to study the phenomena that we see in biology and express our findings in a quantitative way. So, we learned some simple functions in the previous lecture. We learned a linear function where it was y is equal to mx, for example, the y and x. It was a linear function, the line, and we said we learned an equation y is equal to mx. So, if we want in an experiment, if we do, for example, there will be various situations as we discussed, where y is increasing with respect to x. For example, concentration would increase, or the position would increase with respect to time, concentration with respect to position, and so on and so forth. Now, this is a linear function, and if you do other experiments, you might find that the quantity of your interest is increasing not as a linear function, not as a line, but many other ways. So, we would want to learn many function, or we might get an experiment many different types of graphs, as when we plot y is equal to y and x, we had just linear graph, but there could be many other graphs. You could think of some graph which would look something like this, or some other graph which might look something like this, or many different ways y can change with respect to x. And how do we write equations for this? How do we mathematically quantitatively convey that y is increasing with respect to x, but in this particular way? So, if you want to precisely tell how y is changing with respect to x, we would have to learn many more functions. Just like in a language we have to learn many words, we have to have a great vocabulary to say various things that we want to convey. In here too, we would want to use and learn many functions. So, today we will learn a few more functions which we can use to convey the things that we see in experiments or in general in nature around us. So, we will go beyond the linear equations. So, if we go beyond linear equations, what is next? So, we had y is equal to x and y is equal to 2x and y is equal to 3x, and in general y is equal to mx. If we want to go beyond this, we could say y is equal to x square. So, this is a non-linear function where there is a square, x power 2, right. So, how do we plot it? Many of you would know this. So, here is y is equal to x square. So, just like we did earlier, we can make a table. Anybody can make a table if you have a calculator. For any x value, you can write a y value, and the y value is square of x. 0 square is 0, 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16. So, corresponding to y is equal to x square, we can make a table, x in the first column, y in the second column, and y is equal to x square is the function, and we write the square values in the second column, and we can plot x versus y, and the plot would look like this, where we have in the x axis y values plotted, which is in the second column. In the y axis we have the second column, and the x axis, which is the first column here. So, in the x axis we have 0, 1, 2, 3, 4, 5, and corresponding to 0, y is 0, 1 square is 1, 2 square is 4, which is just below 5, 3 square is 9, which is close to 10, 4 square is 16, just above 15, and 5 square is 25. And if I plot this, you will get a curve which looks like this. So, this is how y is equal to x square would look like. So, whenever you hear y is equal to x square, the first thing that would come to your mind, or the first thing that should come to your mind, is it is a function which is a curve like this. This is y and this is x, which is a curve like this, unlike a straight line that we drew last time, which is y is equal to x, which was a straight line, we will compare y is equal to x and y is equal to x square. So just like we did last time, to say there are different ways of representing this. In people would write y is equal to x square in some textbooks. Somewhere you might see y of x is equal to x square. In some other context you might see f of x equal to x square, and all of this have the same meaning as we said. Now we saw here only one part of y is equal to x square. So in this graph that we have it here, we have y is equal to x square, where we had only the positive values of x. But we might also want to plot the negative values of x, that is, we started from 0. So what if x is minus 1, right? So if x is minus 1, minus 2, minus 3, we can examine that. So if x is minus 1, minus 1 square is plus 1, minus 2 square is 4, minus 4 square is 16. So we have minus 4 to plus 4, and if we take that and plot that here, so minus 4 square is 16, minus 2 square is 4, minus 3 square is 9 here, minus 1 square is 1, here again 1, 2 square is 4, 3 square 9, 4 square 16, 5 square 25. So the interesting thing is one should note the symmetry. So what is the symmetry here? So let me plot here. So what we have, we are plotting the both minus side and plus side of this. So this is 0 and this is negative and this is positive, and it looks somewhat symmetric. What does it mean? Whatever be the x value, if x value is 3, there will be 9. So if this is 3, this is 9. The corresponding x value for if minus 3, if x is minus 3, the y is also 9. So if x is minus 3, so this x is equal to minus 3, this x is equal to plus 3, y in both cases y is 9. So y for x is equal to y of 3 is same as y of minus 3, which is 3 square. So this is the symmetry. When x is put as minus x, the function is exactly the same. That you can see just by examining the function. And I want you to understand this symmetry thing a little bit carefully, because very often y is equal to x square, that is, whatever the x value you put, we are finding the square of this. Now instead of x, if we put minus x, instead of x, if we put the minus x, we will also get the x square. So minus x square is also x square is also x square. So the point here is that whether you put x or minus x, y value is exactly the same. So this is a symmetry. And here, because of the symmetry in the curve that we have in this computer, this will look symmetric on either side. So it looks like nicely symmetric. Whether you take plus 2 or minus 2, it is the same value. Plus 4 or minus 4 is exactly the same value. So there is a symmetry around 0. So the symmetry is y of x is equal to y of minus x. This is important to understand the symmetry, and this is why I am stressing, because in future there will be many functions for which the symmetry is important, and we will stress on the symmetry because symmetric functions will have some properties which we will make use of in the future. So I want all of you to carefully understand the symmetry that y of x is y of minus x in this case when function is x square. Now let us compare. So we understood y is equal to x square. Now we can think of just like we had earlier, we can have y is equal to 2x square. So we had y is equal to x square, and we can think of y is equal to 2x square or 3x square. In general, y is equal to mx square or any number here and x square. So let us compare here y is equal to x square and y is equal to 2x square. So the green curve here is y is equal to x square, and the red curve is y is equal to 2x square. So as you can see, when x is 0, both are same. It doesn't matter what the constant is. Y is same when x is 0, 2x square x square. When y is 1, when x is 1, y is 1 here, here it is 2. When it is 2, this is 4, while this is 8. Similarly, so y is equal to 2x square will be above y is equal to x square. So this will go above this curve, and this is how it will look like. And you can think of, if it is y is equal to 3x square, it will go further above. So you can imagine that y is equal to x square, if it looks like this, 2x square will go above this, 3x square will further go above this, and so on and so forth. So you can think of more in general, y is equal to mx square. The shape will be the same. The curve will look roughly this shape. Okay. Now we know y is equal to x and y is equal to x square. How will that compare? If we plot y is equal to x and y is equal to x square, the linear and the curve. So here is y is equal to x, which is the blue line. Y is equal to x square is the red curve. You can see that 0 at x equal to 0, both are same. When x is 1, here they are the same, because x square, which is 1 square, and 1 are the same. They have the same y value, so that's why it's same. But above 1, x square is much larger than x. As x goes to 2, 3, 4 and so on and so forth, x square will have much larger value compared to x. But when x is 0.5, 0.5 square is 0.25, which is smaller than 0.5. So this is important to note that y is equal to x square is smaller when x is less than 1, which you can appreciate when, so you have y is equal to x and y is equal to x square at 1. So this is x equal to 1 and this is y is equal to 1. But when x is equal to half, 0.5, y in this straight line, this is y is equal to x, while this is y is equal to x square. So in this x square curve, which is this curve, this value, this has to be roughly 0.25. Since I drew this, the axis values may not be very nicely scaled, but you can imagine that this is less than 0.5. This is below 0.5. Similarly here 0.1 square and 0.2 square and so on, you can think about it. So the point here is that when x is less than 1, the y value is below this blue curve, and when x is larger than 1, the x square curve is above the blue curve. So this is the thing that you should understand. Now such functions, for example, y is equal to x square, is called a quadratic function, because the second power is called the quadratic function, and there are many cases where that we can think of this quadratic function coming. For example, if you have a spring-like molecule and the energy of a spring we write as half kx square. So energy stored in a spring-like molecule is half kx square, which is an example of a quadratic function. And another example would be surface area of a sphere like cell or an organism having a sphere like shape, and if it has a radius r, the area is 4 pi r square. So, this is also a quadratic function. So, if you plot a versus r, this will look like a constant times r square, and this will look like the function that we look like. So, if we want to plot the area versus the radius of a cell, even if it is approximately assumed to be spherical. So, if you want area versus r, and we know that the area is 4 pi r square, and as you can imagine, it will look like this, some function like which increases with respect to r, and this will look like this. Okay, so that is the quadratic function. Now, if we go beyond, of course, we have cubic function. So, what is cubic function? Y is equal to x cubed. So, let me write that here. The cubic function is y is equal to x cubed. And how will that look like? So, we are going to show that in comparison with x and x square. So, we had y is equal to x, which is the red curve, y is equal to x square, which is the green curve. Now, y is equal to x cubed, which is this blue curve. And as you can see, when x is larger than 1, x cubed value is much larger than x square or x. You can imagine 2 square is only 4, 2 cubed is 8. So, for any x value larger than 1, the cubic curve will go above the quadratic curve or the linear curve. The shape of it is a curve like this, but it goes much above these values. The value will be much above this. So, but when x is less than 1, x cubed is much smaller than other quantities, which I hope you will appreciate. So, when y is equal to 0.1 cubed, right, this is 10 power minus 3, which is 0.001, 10 power minus 3. So, now if you have y is equal to 0.1 square, which is 0.01, and y is equal to 0.1. So, you can see which is 0.1 itself. So, this is smaller than this, which is smaller than this. So, that is what this curve indicates. The blue curve is much below the red and green implies this. So, therefore, what we want to, the curve will look like this, and I urge you to familiarize with this, plot various functions. I urge you to plot x, x cube, x power 4, x power 5 and so on and so forth. I want you to plot. And I want you to also note one more thing, that if you plot y is equal to x cube, what happens when x goes to minus x? So, as we did earlier, so this is x cubed. If I just put x is equal to minus x, this is minus x cubed. Are they equal? We had for the square quadratic function they were equal, but this is minus of x cube. So, they are not equal. So, y of x is not equal to y of minus x here. This is not equal to y of minus x here when y is x cubed. Rather, interestingly, what you can see here is that this is minus x, so this is x cubed. So, this is minus x cubed. So, y of minus x is minus y of x. So, I want you to write this. I want you to see this, and let me write this thing here a little bit carefully. So, I want to write here one thing. What I am going to write is y of minus x. So y of minus x. So let me write this again. So we had y is equal to x cubed, and you want to y, so our function is x cubed. Now we want to write y of minus x, and we saw that this is minus x cubed, and what we want to say is that y of minus x is equal to minus of y of x. I want you to think about it and get used to this kind of language. What I am trying to say is that minus x cubed is nothing but put a minus sign and minus 1 times x cubed, which you can see here. Think about it. Only by thinking about it you will learn this. Familiarize yourself with this kind of language, that y of minus x is minus y of x, which means that minus x cube, which is y of minus x, is minus 1 times x cube, right? Minus 1 times x cube. That is what it essentially we are saying, and therefore this is we can, that symmetry of y is equal to x square is not here, but there is a different kind of symmetry, or there is anti-symmetric if you wish, and we will come and discuss that later. So there is a inverse, there is a different symmetry here which we will discuss later, but I want you to think about it a little bit. Okay, so what I wanted to say next, so we can have other functions now. Y is equal to x power 4. So the next function could be y is equal to x power 4. So this also will look like a function which is increasing, which will increase much faster or much above x square and x cube, and this will have that symmetry that if you put x to minus x, this will look symmetric, therefore it will have its own property, and I want you to think about this. So you can have various functions, y is equal to x, x square, x power cube, and various combinations of x, x square, x cube and all that. Now what happens if you sum one or two such functions? For example, you can think of y, instead of just taking x or x square, you can think of x plus x square, or y is equal to x minus x square, or y is equal to x minus 2x square. Various functions one can think of which are some combinations of these things, or it could be y equal to x minus x square plus 3x cubed. So one can think of combinations of x, x square, x cubed, etc. So this is what we will explore next. So these are more functions which essentially can be written as some combinations of x, x square, x cube, x power 4, etc., which we know how to plot now. You know how to plot x, x square, x cube, etc. Now how will these combinations look like? It turns out that most of the experimental curves that we see in, like you do an experiment and you get some curve, and most of the experimental curves that we get can be obtained by appropriately adding and subtracting these simple functions. If you add and subtract, we can get some curves which would represent typical experimental curves. Or in other words, you get some experimental curve, it can be written as some combinations of x, x square, x cube, etc., and we will see how this can be done, and that's what we will discuss now. So one important function that we will learn today is called the exponential function. You might all have seen on calculator this function exponential e power. So y is equal to e power x. So you all can take a calculator and take an x value, let's say 1, 0, and put on a calculator e power 0 and make a table, e power 0, e power 1, e power 2, and then plot that values on a table, and then you will get a curve like this. Interestingly, note that e power 0 is 1. So I want all of you to understand, this is very important to understand. e power 0 is 1. E power 0 is 1. This is the, it can also be written as exponential of 0 is 1. So that is why you start when here the y-axis in the curve y-axis would start with 1. So in the graph in the computer we will have y-axis starting with 1. So when x is 0, y is 1. When x is 1, y would have some value and so on and so forth. So this curve you should reproduce by taking a calculator and plot it yourself by making a table like we did earlier, and do plot this yourself in a graph sheet, and this often either represented y is equal to e power x or f of x is equal to e power x, and it turns out that this function can be written as a linear combination of all this 1 plus some combination of x square and all that. It turns out that that linear combination is 1 plus x square plus x cube plus x power 4 plus x power 5 let me repeat. E power x can be written as 1 plus x square by 2 plus x cube by 6 plus x power 4 by 24 plus x power 5 plus 120 plus an infinite series. So this is an infinite series where we add all powers of x appropriately weighted by factors like half, 1 by 6, 1 by 24 and 1 by 120. It turns out that if we write such a infinite series, one will get e power x. In other words, e power x can be written as an infinite series like this. How and why? We will discuss that later, but at the moment it is sufficient to understand that one can write e power x as an infinite series like this. So we learned, and one more thing which I want to say is that if you look at for very large value of x, this is increasing and going to infinity. So e power infinity is infinity. This is another thing which I want you to learn. When x in this curve goes to infinity, this function also will go to infinity, it is increasing and it will reach infinity. So e power infinity is infinity. So these things I want you to understand. We will come and learn again in the next lecture how this exponential function can be written as 1 plus x square and what does it mean, how does this series, what is the meaning of this infinite series, etc. we will learn in the next lecture. So in this lecture we will summarize with the following thing. So what did we learn? So we learned quadratic function. So this is our summary. We learned cubic function. Second thing we learned is cubic function, and we learned combination of, we briefly talked about combination of x square, x cube, etc. And we will continue along this line, and we said that e power x can be written as a combination of this, which we briefly mentioned. We will expand on this in the next lecture, and we will see how we can learn about exponential function using this expansion, and how we can use other functions as a combination of x square, x cube, etc., which we now know how to plot. So we will continue in the next lecture. Bye.